Hello, welcome to a new lesson where we are going to talk about Legendre Polynomials. Okay, and recall that whenever you start studying some famous polynomials that are maybe in the course of special functions, you always wonder what happens with orthogonality, right? Recall that we can say that a set of polynomials is orthogonal whenever we take two elements and calculate the inner product between these two elements, and we get zero if these two elements are different, but we are going to get something different from zero if these two elements are equal. Okay, so we are going to start by defining a function u of t as t squared minus 1 to the n. Okay, and later on, we will use this notation to remark the n derivative of this function. We will name this as u to the n of t, right? Recall that if this n is in parentheses, it denotes the n derivative of the function, okay? So this will be the derivative with respect to t n times of t squared minus 1 to the n. Okay, perfect. So what are we going to do? Well, to be able to use this in the orthogonality proof, we are going to show first that the 2n derivative of this function t squared minus 1 to the n is going to be equal to 2n factorial. Okay, so we are going to start with the proof, and we are going to use this definition over here to establish that using the binomial formula, we are going to have that t squared minus 1 to the n is going to be the sum from k equals to 0 up to n of n choose k, and then it will be minus 1 to the n minus k times t squared to the k power. Okay, so with this expression, we are going to take the 2n derivative with respect to t of this, and this will be equal to, well, the sum, and we are going to take the derivative of this element only because it is the only one that depends on t, right? And the derivative is with respect to t, so we will have the sum from k equals to 0 up to n choose k minus 1 to the n minus k, and then the 2n derivative with respect to t of t to the 2k. Okay, perfect. So what is going to happen here? We can see that if we take the 2n derivative with respect to t of this, what happens if n is equal to k? Well, we are going to take the derivative. For example, for the first element, it will be 2k, and then 2k minus 1, then 2k minus 2, all the way up to 1, right? And then t to the 2k minus 2n. But if n is equal to k, of course, this is going to be equal to 0. And then we will have a 2k factorial over here. Okay, perfect. But looking that k is equal to n, we will have that this is 2n factorial. Okay, perfect. Another case we can have is that, well, maybe the n is bigger than k. In that case, we will get to the derivative with respect to t of some constant, right? And then when we take the derivative again, this will be equal to 0. Okay, but that is in the case where n is bigger than k, but we are not going to be interested in that case for now. So after showing this, we are going to start by proving that the Legendre polynomials are orthogonal. And to do that, we are going to introduce the definition of Rodriguez of the Legendre polynomials that says that the n-order Legendre polynomial is equal to 1 divided by 2 to the n factorial, and then the derivative n times of t squared minus 1 to the n. Okay, so from here we can say that this is p sub n of t is equal to 1 divided by 2 to the n factorial, and then u to the n of t, right? Where this is the n derivative of u, because we have the u over here. Perfect. So with this, we can say that un of t is equal to 2 to the n factorial p sub n of t. Okay. So we are going to start by proving the orthogonality property in the interval -1 to 1. Okay, this will be the interval of definition for the Legendre polynomials, and therefore it is the interval of definition of the orthogonality property. So we are going to have, for example, the inner product between two Legendre polynomials with this factor, right? So we are going to start by saying that m is different from n, and without loss of generality, we are going to consider that m is less than n. Okay, perfect. So what are we going to do? We are going to start by taking the integral from -1 to 1, okay, of 2 to the n factorial p sub n of t, and then we are going to consider like a general polynomial t to the m, right? If we are able to show that p is orthogonal to t to the m, then p will be orthogonal to any polynomial. In particular, it will be orthogonal to the Legendre polynomials. So we are just going to consider by simplicity that we are proving the orthogonality with a polynomial t to the m. Okay, and of course, this is dt. Perfect. So this is going to be equal to the integral from -1 to 1, and recall that this is the definition interval of the orthogonality property, the -1 to 1, of course. And then here we can say that this is equal to u to the n of t, and then t to the m dt. Perfect. So this is leading us to integrate by parts, right? Because if we consider this as u and then this as db, we'll see that if we integrate by parts m times, then this t to the m is going to disappear. So what are we going to get? This will be equal to u, which is t to the m, and then b, which is u to the n minus 1 of t, right? Because if this is our db, we need to take the integral of the n derivative. So that will make to have a derivative like eliminated from here, right? So it gives us u to the n minus 1, and this is evaluated from -1 to 1, and then minus the integral from -1 to 1 of the u, which is m times t to the m minus 1, and then again b, which is u to the n minus 1 of t dt. But if we remember the definition of u of t, of course, we know that this will be equal to 0, because if we evaluate this as, well, at t equals 1 and -1, this will be equal to 0, right? So this whole piece is going to be 0. Perfect. So what happens if we integrate by parts again? Well, we are going to consider this as the u, and then this as db, and then this will take us to a minus here, and then u, which is going to be m2 times t to the m minus 1, and then b, which is u to the n minus 2 of t, just by the same reason we mentioned before, evaluated at -1 and 1, and then minus the integral of m times m minus 1, t to the m minus 2, and then u to the n minus 2 of t dt. Okay, perfect. So if we simplify a little bit, we will get that this is m times m minus 1, and then the integral from -1 to 1 of t to the m minus 2, u to the n minus 2 of t dt. So I think it's not very hard to notice that if we keep going m times, okay, we are going to get that this is -1 to the m, right? Because at the first step, we had a minus here. And then when we integrate again, we took another minus out. So that gives us minus 1 squared. But if we do it m times, we will get a minus 1 to the m because, well, yeah, we are taking a minus sign every step we do that. And then this will multiply an m factorial, right? Okay, and then we will have an integral from minus 1 to 1 of t to the m minus m, but this will be 0, which is going to be equal to 1. So that element disappears, and we will have here that we need to calculate the integral of u, but the n minus m derivative of u, right? dt. So, yeah, I think this is already a very easy integral to evaluate because we are going to get just that this is minus 1 to the m factorial. And then if we take the integral one more time on u, we will get that this is u to the n minus m minus 1, evaluated from minus 1 to 1. Okay, but by the same reason, we can see easily that this thing is going to be cancelled. Recall that u of t is defined as t squared minus 1 to the n. And if we evaluate at minus 1 and 1, this will be equal to 0. So finally, the conclusion is that this is equal to 0, meaning that, well, the Legendre polynomials are orthogonal with the polynomial t to the m. And in particular, if t to the m represents another Legendre polynomial, we will have that, well, these Legendre polynomials are orthogonal, or are at least the inner product between the Legendre polynomials is equal to 0 if m is different from n. So that is the important thing. At the end, we will write the conclusion explicitly. Perfect. So we are going to be interested now in the case where m is equal to n. So what happens in that case? Well, we are going to remember that p sub n of t is equal to 1 divided by 2 to the n factorial, and then the n derivative of u, right? So from here we can say that u n of t is equal to 2 to the n factorial p sub n of t. And we are going to take the inner product of two functions u. Okay, so this will be minus 1 to 1 of 2 to the n factorial squared pn squared of t dt. Okay, so we need to be able to evaluate this integral to see what are we going to get if we take the inner product between two Legendre polynomials. And we can just ignore this element because it is a constant. So at the end, we will be interested in just the integral from minus 1 to 1 of pn squared of t dt. Okay, but I wrote this in this way because we can see this as the integral from minus 1 to 1 of just u to the n of t squared and then dt. Perfect. So this will be equal to the integral from minus 1 to 1 of u to the n of t, u to the n of t dt. And again, we are going to use integration by parts. Okay, in this way, it doesn't matter what are we going to name as u. Okay, so this will be equal to u, which is u to the n of t, times db, which is u to the n minus 1 of t, evaluated from minus 1 to 1. And then minus the integral from minus 1 to 1 of, it will be the derivative of u, right? So this will increase the index here to the n plus 1, and then the t here, and we will have u to the n minus 1 of t dt. So with this element, it is very easy to see that if we keep going n times, this index is going to reach the element to n, and then this is going to reach the element n minus n, which is going to be equal to 0, right? So again, by the same reason, these elements are going to be equal to 0. Okay, perfect. So this will be equal to minus 1 to the n, okay? And then it will be the integral from minus 1 to 1 of u to the 2n of t, and then u, it will be right here the zero derivative, right? But you know that the zero derivative is just the regular function. So we will have only u of t dt. Okay. Okay, and here is where we are going to use the result that we found at the beginning of the lesson. We showed that the 2n derivative with respect to t of t squared minus 1 to the n, well, it is just equal to 2n factorial, where m is equal to n, right? So again, remember that this is u of t, okay? So that means that we can just take this 2n factorial and substitute it here. So this will be 2n factorial. Perfect. So this is equal to minus 1 to the n, the integral from minus 1 to 1 of 2n factorial u of t dt. Okay, so this will be equal to minus 1 to the n, 2n factorial, and then the integral from minus 1 to 1 of u of t. But we are going to use the definition of u of t, that is t squared minus 1 to the n dt. Okay, so this can be seen as minus 1 to the n, 2n factorial, the integral from minus 1 to 1. And we are going to split this difference of squares as it will be t plus 1 times t minus 1, and then these are all raised to the n power dt. Perfect. So again, we are going to use integration by parts. So that is dv, this will be u. So what are we going to get? This will be minus 1 to the n, 2n factorial, and this will multiply u, which is t minus 1 to the n, and then, well, it will be b, right? But that will be the integral of this piece. So what are we going to get? It will be t plus 1 to the n plus 1 power divided by n plus 1, evaluated from minus 1 to 1, and then minus the integral from minus 1 to 1 of, it will be du, right? So we will take the derivative of this, which is going to be n times t minus 1 to the n minus 1, okay? And then the integral of this again, so that will be t plus 1 to the n plus 1 divided by n plus 1 dt, and we close the brackets here. Okay, so again, it is easy to see that if we plug t equals 1 or t equals minus 1 in this piece, well, it is going to be 0. So we can cancel this. Perfect. So we are going to get that this is minus 1 to the n, 2n factorial, and look that we have a minus here. Okay, so we can just add it to this minus 1 to have minus 1 to the n plus 1, and then the integral, well, we have another n divided by n plus 1 here, and then the integral from minus 1 to 1 of t minus 1 to the n minus 1, t plus 1 to the n plus 1 dt. Of course, we are going to keep going n times. So if we take the derivative n times of this, we are going to reach the element t minus 1 to the n minus 1, which is going to be 1. And then if we keep going with this, we will get the element t plus 1 to the 2n. Perfect. So what are we going to get if we do it again? This will be minus 1 to the n plus 1, 2n factorial, n divided by n plus 1, and then this will multiply, taking again this by u and then this by dv. It will be t minus 1, and then t plus 1 to the n plus 2 divided by n plus 2, minus the integral from minus 1 to 1 of the derivative of u, right? So that will be n minus 1, t minus 1 to the n minus 2, and then t plus 1 to the n plus 2 divided by n plus 2 dt. Okay, again, this is going to be, well, this is evaluated from minus 1 to 1, right? And this is going to be equal to 0. So this will be minus 1 to the n plus 2, right? Because with this minus, we can increase the exponent of this minus 1 to get 2 to the n factorial, then n times n minus 1 divided by n plus 1 times n plus 2 by this element. And then the integral from minus 1 to 1 of t minus 1 to the n minus 2, and then t plus 1 to the n plus 2 dt. Okay, so I think that with this is going to be easier to see that if we do it n times, this will be minus 1 to the n plus n, but that will be 2n, right? But minus 1 to the 2n is just going to be 1. So we can cancel this minus 1. And then this will be 2n factorial, and then n times n minus 1 all the way up to 1, but that is n factorial again. So this is divided by n plus 1 times n plus 2 all the way up to 2n. And then the integral from minus 1 to 1 of, well, it will be t minus 1 to the n minus n, but that is t minus 1 to the 0 power, so we will only get a 1 here. And then this other element, it will be t plus 1 to the n minus n, so that is 2n dt. Perfect. So with this, we only need to integrate just one more time. So what are we going to get? It will be 2n factorial divided by n plus 1 times n plus 2 all the way up to 2n. And then what is this going to be? It will be t plus 1 to the 2n plus 1 divided by 2n plus 1, and then evaluated from minus 1 to 1. Okay, perfect. So here we are going to make a trick. You can notice here that if we multiply this by n factorial here, this whole piece is going to become 2n factorial. Okay, it's not hard to notice that. Okay, so if we do that, we need to multiply here by an n factorial, right? Just for not to break the equality. Okay, perfect. So we will get something like this: 2n factorial squared, and then divided by 2n factorial here. Perfect. Of course, this is in order to cancel these 2n factorials. And then if we evaluate from minus 1 to 1, we will have that at minus 1, we will have 0, right? But when we evaluate at 1, this will be 2 to the 2n plus 1 divided by 2n plus 1. Okay, perfect. So this will be n factorial squared, and then times 2 to the 2n plus 1 divided by 2n plus 1. Okay, and remember that this whole thing is just equal to this integral that we have here. And we are interested in calculating the integral from minus 1 to 1 of p sub n squared of t dt. Okay, so we just need to take this element dividing to the other side of the equation. Okay, so again, this is equal to the integral from minus 1 to 1 of 2 to the n squared n factorial squared p n squared of t dt. So this leads us to the integral from minus 1 to 1 p n squared of t dt equals to, what is this going to be? It will be n factorial squared 2 to the 2n plus 1 divided by 2n plus 1, and then this is divided by 2 to the n squared n factorial squared. Okay, so we can cancel this n factorial squared over here to get that this is 2 to the 2n plus 1 divided by 2 to the 2n times 2n plus 1. Okay, but we can see this as a 2 to the 2n times 2. So to cancel these elements, and to get that if m is equal to n, then the integral from minus 1 to 1 of p sub n of t, p sub m of t dt, which will be equal to this integral over here, is going to be 2 divided by 2m plus 1. Okay, perfect. And remember that if m is different from n, then the integral from minus 1 to 1 of p sub n of t, p sub m of t dt is going to be equal to 0. Okay, so this proves that the Legendre polynomials are orthogonal. Recall that if we take two different polynomials and calculate the inner product, well, they need to be equal to 0 to be orthogonal. So the Legendre polynomials have that property. Perfect. So I think that this will be the final important result of the lesson. Later on, we will use this result to define what are the Fourier Legendre series in the course that we are making about Fourier analysis. Perfect. So I think this is a good moment to finish the lesson. I hope you enjoyed it, and thank you so much.